Thank you for joining us today for the Sharing GPUs Without Flying Blind webinar. My name is Daniela, and I'll be the moderator for today's session. I'm excited to introduce Julian, who is the head of Kubernetes engineering here at Kubex, who will lead today's session. Hey, Julian. Julian will take us through a few slides and then get right into a demo. And with that, I'm going to pass the mic over to Julian to get us started.
Thanks, Danielle. All right, so welcome everyone, and thanks for joining us today. Today we'll be talking about GPU sharing, and the title says without flying blind because that is the real challenge here. Once multiple workloads land on the same physical GPU, the old mental model of one pod, one GPU starts kind of breaking apart. And all the assumptions we have around how CPU and memory are shared on Linux kind of also break down as well. So we'll start by understanding some of the GPU sharing technologies such as time slicing, MPS, and MIG. Then we'll look into where open source Kubernetes native project fit. And one important distinction that we will be coming back to is that scheduling a fraction is not the same thing as enforcing a fraction of a GPU. And by the end, the goal is that not everyone here picks the same technology. The goal is that everyone here understands the GPU sharing patterns and pick what is right for each use case. Quick intro, I'm Julian, head of Kubernetes engineering here at Kubex. I head the organization that builds automation for container and GPU-backed infrastructure. I am also a technical lead within the Developer Experience Technical Advisory Group within the CNCF. For everyone that is less familiar, the CNCF is an open source foundation behind many of the cloud native projects we use every day within the Kubernetes ecosystem, including Kubernetes itself. In this session, we'll be touching on a few CNCF projects that are becoming relevant to GPU sharing in Kubernetes. This slide here is our agenda for the session. We'll be staying practical and not go into vendor feature comparison. Our biggest focus here will be on what GPU sharing means on Kubernetes and how to make it work well. The key theme is that the workload should drive the decision. Latency, memory behavior, isolation requirement, and workload behavior while sharing a GPU matter more than a generic target utilization number. And then once the sharing is enabled, our job is not done. We need to know what the fraction really buys us, what it does and doesn't guarantee, and then what to watch so that sharing doesn't become guessworky. First, let's understand why GPU sharing is important. The running LLM AI workloads on Kubernetes focuses a lot on the training jobs as well as running the inference. So training is used to create the LLM and uses batch jobs you size once and run to completion. They go as fast as they can, and giving them full GPUs makes a ton of sense there. But inference, which is serving the LLM, is not like that. It's more like a service. It behaves like a web server where load follows how people actually use the product, so demand moves throughout the day. So we see it here where our usage peaks in the middle of the day, but the reserve line that is at the top is flat because we hand out whole GPUs. And the space between those two lines is capacity that we pay for and that we don't use. So then one will ask, if it's so obvious, why are we handing out full GPUs for those use cases? But unlike CPUs, the Linux kernel and Kubernetes, they have no native way to give a pod a slice of a GPU and hold it to that boundary. So sharing GPUs isn't in the core primitive of Kubernetes. And the mechanisms that do exist for sharing are vendor specific, and they have several sharing options per vendor, and they each have their pros and cons. Also, sharing has been hard to configure and even harder to observe in Kubernetes. So a full GPU card is usually the safer choice. And that was fine when capacity was cheap and easy to get. But with GPU inventory being limited in cloud providers and considering today's prices, finding a way to be more efficient with the GPUs we have became even more critical than it was. So fixing the gap on this chart is the problem that the rest of the session is about. In Kubernetes, a GPU fraction is not a supported unit. Many solutions exist to take those fractions, and they hide behind very different guarantees depending on the mechanism you'll be choosing. So quarter GPU might mean one of several things. It could mean access to the compute of the GPU 1/4 of the time. Could mean the scheduler in Kubernetes is accounting a value that says this workload should fit beside others because it uses 25% of the GPU, and there is enough remaining shared capacity on the GPU for it. Could also mean having 25% of the GPU memory reserved to the pod, enforced by some software, or it could also be a hardware partition with strong isolation that is roughly 25% of the GPU. And all of those things are very different operational promises. So when someone asks, can I give this workload 25% of a GPU? The better question is, what do you need 25% to mean? Is it throughput? Is it memory? Does it need isolation? Do you need best effort or guaranteed performance? And what is the most important thing? Is it cost or is it performance? This slide here is the mental model for the rest of the talk. The important distinction here is that there are two very separate jobs that need to be accomplished. First, we need to do the orchestration. That is the Kubernetes side decision. Where does the workload land? Which queue or team does it belong to? Does it need to do gang scheduling? What priority does it have? And how much GPU capacity should we account for? And then we have a fractioning. This is the runtime or hardware side decision. Once the workload is on the car, what actually prevents it from using more memory, more compute, or more isolation than intended? The scheduler can make a placement decision. It can say the pod should get a fraction and should share the GPU with these other pods, but that doesn't mean that it automatically enforces that fraction either. And this is where the bottom line here that we have in the slide matters. A scheduled fraction is not an enforced fraction, and a decision must be taken on how to enforce it. There are more options than the one we see here. And the same principles still apply if you use another scheduler, device plugin, or vendor-specific mechanism. But today we'll be focusing on NVIDIA and the mechanisms that allow to do the fractioning on it. First, one thing to keep in mind is that from an orchestration and Kubernetes scheduling point of view, the GPU is modeled as a resource that is allocated as a whole. It's not a fully managed resource like CPU or memory. And that's why there are various technologies that allow us to perform the sharing. Let's compare the three primary ways of sharing a GPU with NVIDIA. Kind of a useful way I like to think about them is three ways of sharing a kitchen in a restaurant with several cooks. With time slicing, several cooks share one single stove. They take turns using it, and nothing prevents a cook from using the stove longer than it should and from taking over all the burners for themselves. There's nothing that is controlling that. So translating that to GPU, a workload gets access to the GPU, but that doesn't guarantee a fixed percentage of compute or memory. It may use more and nothing prevents it from doing so. Big goes at the opposite end and divides the kitchen into complete separate stations. Think of it like a cooking competition where each participant gets their own little dedicated station in the big kitchen. Translating that to GPUs, each workload receives dedicated compute and memory resources that the others cannot consume. But the big trade-off that we have to do here is that the station sizes are fixed before the workloads arrive, and changing the size of those stations is not trivial. So specifically for MIG, we need to pre-decide how to partition the device. If the partitions need to change in size, the device must be reconfigured and repartitioned. NPS kind of lives a little bit in the middle there. It has the cooks coordinated through a kitchen manager. So they all work within the same kitchen, that is the big kitchen there. They all work at the same time, each on their burner of the stove, but the kitchen manager is kind of keeping everyone in line. So everything becomes much more organized, but every action needs to go through the kitchen manager. If the manager isn't there anymore, then everything stops working. So translating that to the GPUs, we have multiple workloads and they have to talk to an NPS control daemon that coordinates who is using the GPU and how much memory and compute each workload can use. So overall, the key distinction is what is being shared and where the boundary is enforced. Time slicing shares access with little to no controls. NPS shares the GPU concurrently with software level controls via the NPS control daemon, and MIG creates hardware isolated partitions. Let's look into an overview of what each sharing mechanism gives us. For the first 2 points, we've just looked into how each technology handles sharing and allocates workloads. Now, giving multiple workloads access to a GPU via time slicing gives no compute or memory reservation. NPS adds a software control to ensure fairness, and MIG makes it a hardware boundary. The key trade-off here is flexibility versus predictability. You need to choose based on the guarantee that the workload cannot afford to lose. Now, if we look at this here, time slicing is the easiest baseline, and it doesn't require any specialized GPU hardware, but we see that it has many limitations. Now let's look into how we can add workload-aware sizing and enforcement around it to make it better. The problem is where the number lives. The most common approach for NVIDIA time slicing in Kubernetes is to have the split configured on the node through the NVIDIA device plugin. The workload still asks Kubernetes for one GPU. It cannot say I need 0.30 or 0.45. It only lands on a node whose GPUs have already been divided into equal replicas. So the key change that we want to do here is to set where the fraction is defined. With basic time slicing, the cluster administrator chooses that fixed number of replica for every GPU. The workloads request one or more of these slices, but they're still choosing from a cluster-wide configuration. Changing the size means the plugin has to be completely reconfigured and rolled out through the nodes. The Kai scheduler, which is a CNCF project, moves that decision into the workload. One pod can ask for 0.22 of a GPU, another for 0.38 of a GPU, and Kai can place them together as long as the total fits. So that gives us much finer grained packing without pre-partitioning every GPU. And then under the hood, Kubernetes still understands whole GPU resources. Kai uses a reservation pod to claim the physical GPU from the default scheduler and then keeps its own accounting for the workloads that are sharing. Now, one important caveat is that this fraction is an allocation and scheduling unit. It doesn't automatically guarantee the same percentage of compute. Flexible allocation is useful, but we still need something to enforce the boundary at runtime. And that's what we'll look into the next slide. All right, so this is what it reference architecture. It's not the only correct one. Here, Kai handles the orchestration side. It decides the placement, applies queues and quotas, respects priority, and keeps track of how much of the GPU each workload has requested. At admission time, Kai integrates with HAMi core to inject a C library that will ensure that the container stays within its allocated memory fraction. This combination uses HAMi core and not the full HAMi scheduling platform, which is also a CNCF project as well. So you could replace parts of this architecture depending on the workload. NPS could provide per client memory and compute control. Big is the better fit when the boundary must exist in hardware. And HAMi can also provide its own scheduler instead of using Kai. But the combination we've got here goes on top of time slicing and provides memory limits safely so that pods don't go beyond their own memory fraction. It doesn't limit the compute fraction of the GPU, which is something we'll look at solving outside of Kai and HAMi core. But overall, the idea is the separation of responsibility. One layer places and accounts, that's Kai, and another layer enforces, that's HAMi core. Device level utilization was often enough when one pod owned the entire GPU. But once several workloads start sharing the card, it stops telling the full story. So a GPU being used at 90% of the time can be a good thing or a bad thing when it's shared. If two pods were scheduled with fractions that sum up to 50%, but the utilization is at 90%, that means the scheduler risks adding more pods on that GPU and creating contention. And that's where our Kubex exporter comes into play. It looks at GPU utilization at the process level and correlates it to the container and the pod. That way we can continue to track resource utilization at the pod level accurately. You can currently use it for free, and it will also be open source soon. It plugs into your existing Prometheus deployment to give you this added visibility. Another important layer is to ensure that you have the appropriate application metrics. This will complement the resource utilization metrics to understand any impacts to performance when you start sharing your GPUs. Now, the fraction that we choose at admission time is really just a prediction that we have about future demand. Even a good initial estimate will eventually become wrong as traffic models, batch sizes, and many more things start changing. Fraction management needs to happen in a control loop instead of being a one-off thing. We observe the workload, we establish the baseline, we choose a safe target, we add headroom, and then we continue watching both GPU demand and application health. So then when the evidence is strong enough, we can start upsizing or downsizing to rebalance the resources for the workloads so that it stays representative of the real usage. The loop itself is straightforward. The guardrails that we have here are what make it safe. In practice, we usually want to grow allocations quickly when an application is at risk and then shrink them more cautiously. So now let's look at how this works in our demo. Here we're in the Kubex UI. We see our overall GPU utilization that we'll have here, and then we'll start diving into one specific workload and look into it. Let's look at one of our VLLM containers that we have here. I first want to look at one container that we haven't yet optimized. So here we have a VLLM pod that is serving inference. And then we can see that the current average utilization of the GPU for that specific container sits at roughly 6% for the compute utilization, and it peaks at around 27%. And the GPU memory is even lower. It averages at about like 3.5% and peaks at 17%. So there is a clear underusage of the GPU that exists here and a clear opportunity for doing an optimization using GPU sharing. What we're doing here, we're saying, let's recommend to use a fraction that is 0.375 here, using the exact same GPU, just start fractioning it. And then we can have an average utilization that jumps to 15.7% and it peaks at 72%. So we're still staying safe. We're still having headroom, but we're getting much better GPU utilization. Memory utilization will also be more efficient as well, but we have to round up to the thing that we use the most, which is compute. Looking into the details, we see we're already using the Kai scheduler, so that's a good thing. The only thing we're saying that we're changing is we're going from one whole GPU to a fraction of a GPU, which will result in less memory being used as well. That means that we can go from a monthly cost of about $1,100 here to $439. Let's look at a container that has been optimized and let's see what the story tells us here. We see we have the same container here. This one has been using GPU sharing. And if we look at its utilization pattern, here is what is interesting. We see here the orange line at the top kind of represents the allocation of this GPU that we have. So it was previously using one whole GPU. We started enabling fractioning here. So fractioning here, the resource utilization was even lower than it is now. So it was able to size it to 0.25 of a GPU. But that's where the control loop starts being very important, where we're monitoring continuously the resource usage of the GPU to make sure that we have a representative fraction of the resources being used. The loop here detects that, oh, the GPU usage is starting to go up. Let me actually upsize this fraction so it stays with enough headroom and doesn't start creating contention on the GPU because it's going beyond its allocated fraction. We see that it jumps here to 0.375 after. So by using this control loop, we're ensuring that we're always getting an accurate GPU fraction that is assigned to the GPU. And that's what's important for operationalizing this safely. Here's our final capability blueprint that shows what vanilla time slicing with NVIDIA gives us in Kubernetes and what we can get by adding Kai, HAMi core, and the Kubex solution into the mix. So we haven't reached a perfect solution that fits all use cases, but we've overcome multiple time slicing limitations, including getting flexible Kubernetes native scheduling using Kai, a hard memory runtime cap for our workloads by using HAMi core, per workload resource usage visibility using the Kubex GPU exporter, and then active adaptation for sizing GPU fractions and ensuring fairness using the Kubex platform. So in the end, you choose a mechanism that is based on the requirements of your workload and the available sharing technologies on the GPU and Kubernetes environment you are running in. If you're interested, Kubex offers free trials, so you can try this for yourself and then see how it behaves in your environment. We will be stopping here and taking any questions you may have. And thank you very much.
Thanks, Julian. I do see a couple. The first one is, how do you stop an automated right-sizing loop from reacting to every short spike?
That's kind of important here, where the continuous loop that we have is continuously monitoring the resource usage. It is important to react to the spikes that could be risking to create contention on the GPU. Basically, if memory is the kind of critical point there, and with HAMi core, we're limiting it so that we're not creating OOMs. If the compute goes a little bit beyond its allocated fraction, it can be fine. But basically, the goal is try to upsize fast and then downsize slowly. But for compute, we can actually afford to upsize slowly. And that's something we do in Kubex, where we have policies that are governing how fast or how slowly you may be upsizing, and then how fast or how slowly should you be downsizing as well. So you stay in control of your workload there.
Perfect. Thank you. I've got two more questions. The next one is, does it work with all NVIDIA series?
That's one of the key points of time slicing and using Kai and HAMi core, is that with MIG, you're kind of constrained to hardware that is kind of newer and much more expensive. With time slicing, this is supported on most even commodity hardware from NVIDIA and almost all recent NVIDIA chips. So even Tesla T4s that are available fairly cheaply support time slicing. So that's a good solution to reuse your existing hardware. You don't have to buy new hardware to potentially do MIG partitioning. You don't have to roll out an MPS control daemon either. Time slicing gives you basically a solution for your existing hardware but you have to add these layers to make sure that it's done in a safe way versus just vanilla time slicing that has all the limitations we talked about.
Perfect. Thank you. One more. What happens when a workload needs more GPU capacity, but there is no free space on its current card?
Yeah. So what we do basically in our solution is we realize when we're upsizing and we're saying, well, every time we're upsizing, we're going to do either in place upsizing and then if it fits, but then if it doesn't fit, then we can evict the pod and it gets rescheduled onto another node that has available GPU. Or if you have no available GPU, then it can auto scale up. But we'll basically do it in place if it fits so that the scheduler is able to take that fraction into account, but then evict so that it's placed onto another GPU if it doesn't fit.
Thank you. And those are all the questions that I'm seeing here. So thank you, Julian, for taking us through all this content. Thank you, everyone, for joining us today. Have a great rest of your day.
Thank you, everyone.